Hi students, in the last video we discussed about the vertical oscillations of a spring. In the case of vertical oscillations of a spring, we discussed about the restoring force F is equal to minus K into X. Now in this video we will discuss about what will happen to the spring constant when the springs are connected in different ways. That is combination of springs. Spring constant or force constant is also called as stiffness constant. It is a measure of the stiffness of the spring. If the value of the spring stiffness constant is very large, that means we have to apply a large force to compress or elongate the spring. Similarly, if the value of the spring constant or stiffness constant of a spring happens to be smaller, then it means that only less force is required to stretch either a spring or elongate a spring. That is the main difference. Springs can be connected in two ways. Either the springs can be connected into one end to another end, which is called as series connection of springs, or alternately the springs can be connected in parallel. In this section we are going to compute the effective spring constant of the spring when springs are connected in series and in parallel. Let us first see about the springs connected in series. Take this is a spring and of spring constant K1, and this is another spring of spring constant K2. In this diagram the two springs are connected in series. What do you mean by series connection? In series connection, the term series connection means one end of the spring is connected to one support and the other end of the spring is connected to the one end of another spring of spring constant K2. The other end of the second spring is connected to a mass. So this is called as one to one end connection or series connection. So if you consider here, we have restricted to only two springs. Here this is a spring of spring constant K1 and this is another spring of spring constant K2, and here we have restricted to ourselves to only two springs. Here the two springs are connected in series and the free end of the spring constant spring combination is connected to a mass. And here we can find the effective spring constant. Now the spring combination system is in equilibrium position, that is in X naught. Suppose if you apply the force to this mass and make the mass to move along positive X direction, what will happen? The spring mass system which is connected in series will move through a small distance X and then it will come back. So the spring will undergo oscillations along the horizontal direction. Let F be the force applied towards the right. Since the spring constant for different springs are different and the connection points between them also not rigidly fixed, here you have to note that the strings can stretch in different lengths. That is very important. So when strings are connected in series, x1 be the displacement produced on the, or x1 be the elongation produced in the first string and x2 be the elongation produced in the second string from the equilibrium position due to the applied force. So the net displacement of the point mass point is x is equal to x1 plus x2. So from Hooke's law we can write this diagram represents the combination of springs connected in series. Here F remains the same but x1 and x2 are different. So I can write from Hooke's law F is equal to minus Ks into x1 plus x2, where Ks represents the effective spring constant of the system. So from this equation we can write x1 plus x2 is equal to minus F by Ks. For springs in series connection, F remains the same. So as F remains the same, I can write F is equal to minus K1 x1 is equal to minus K2 x2 using Hooke's law equation. So From this, I can write x1 is equal to minus f by k1, x2 is equal to minus f by k2. Okay, so if you take this expression and substitute in the expression for x is equal to x1 plus x2, I can write instead of x1, I can substitute f by k1 and x2 f by k2. So minus f by k1 minus f by k2 is equal to minus f by ks. I suppose you can able to understand why I am writing this. This is applied in equation x is equal to x1 plus x2. Here instead of x we have substituted minus f by ks. Instead of x1 we have substituted minus f by k1. Instead of x2 we have substituted minus f by k2. It is very, very important. So from this expression f get cancelled on both sides. We can write 1 by ks is equal to 1 by k1 plus 1 by k2, which is equal to k1 k2 into k2 plus k1, which is equal to 1 by ks, or ks is equal to k1 k2 by k1 plus k2 Newton per meter. Suppose we have n springs connected in series, then the effective spring constant in series combination is 1 by ks is equal to 1 by k1 plus 1 by k2 plus 1 by k3 plus etc. up to 1 by kn, which is equal to summation of I is equal to 1 by k 1 to n 1 by ki. If all the springs are having identical spring constants, that is if k1 is equal to k2 is equal to k3 is equal to kn is equal to k, then the above equation can be written as 1 by ks is equal to n by k, or ks is equal to k by n. That means from this equation it is clear that the effective spring constant reduces by a factor n. So for springs in series combination, the effective spring constant is always lesser than the individual spring constants. And from equation 10.39, we can write k1x1 is equal to k2x2. Therefore, the ratio of the compressed distance or elongated distance, that is x2 by x1 or x1 by x2, from this expression is given as x2 by x1 is equal to k1 by k2. You all know that any elongated spring will possess elastic potential energy. The elastic potential energy stored in the first and second springs are respectively u1 is equal to half k1 x1 square and u2 is equal to half k2 x2 square respectively. Therefore, their ratio is u1 by u2 is equal to half k1 x1 square by half k2 x2 square, which is equal to half get cancelled, k1 by k2 into x1 by x2 the whole square. You know that x2 by x1 is k1 by k2. So when you substitute it here, you will get the above equation reduces to k2 by k1. Next, springs connected in parallel. When two or more springs are connected in parallel, we can replace all the springs with an equivalent spring factor or effective spring factor whose net effect is the same as if all the springs are in parallel connection. Consider there are two springs K1 and K2, springs having stiffness constant K1 and K2. They are connected parallel. Here we can able to understand that keeping them one below the other represents the parallel connection. Can connect these two parallel connected springs to a same mass m. So this combination represents the parallel combination of two springs or parallel connection of two springs having different spring factors. Here for our simplicity we have taken only two springs. of spring constants K1 and K2 and attach the springs to a mass M as shown in this diagram. The result can be generalized to any number of springs in parallel. So this diagram and this diagram here remains the same. Here instead of these two springs taken separately, we can consider the effective combination as a single spring, that is spring here having a equivalent or effective spring factor Kp, and this Kp, which is the effective spring factor, which is the combination of the two springs K1 and K2, is connected to a mass M. So this diagram and this diagram are equivalent. Now the net force for the displacement of mass M is F is equal to minus Kpx, where Kp is the effective spring constant. Here the first spring and the second spring are elongated by the same distance. This is very important here. That is, you have to understand that when springs are connected in series, x1 and x2 are different. F remains the same. But when springs are connected in parallel, x remains the same for all the springs, but the force is different. So here we can write F is equal to minus K1x minus K2x, or instead of F I can substitute minus Kpx. So minus Kpx is equal to minus K1x minus K2x. As x and x gets cancelled on both sides, we will finally get Kp is equal to K1 plus K2. That is, effective spring constant of the parallel combination of springs is equal to the sum of the individual spring constants of the springs. When you write it in general form, we can write Kp is equal to summation of I is equal to 1 to n Ki. If all the springs constants are identical, that is when K1 is equal to K2 is equal to K3 is equal to Kn is equal to K, then here I can write Kp is equal to Nk. This implies that the effective spring constant increases by a factor n. But we have seen that when springs are connected in series, Ks is equal to K by n. There it reduces by a factor n, but here it increases by a factor n. Hence, for springs in parallel combination, the effective spring constant is greater than the individual spring constant. Next, we will see about the oscillations of a simple pendulum in simple harmonic motion and laws of simple pendulum. I suppose you all have seen about and heard about a simple pendulum. This is the diagram of a simple pendulum, and this is the pendulum is suspended in a pendulum clock. A pendulum is a mechanical system which exhibits periodic motion. A simple pendulum consists of a bob with a mass M suspended by a long string. The string is supposed to have a mass. The string is a massless and inextensible string. One end of the string is fixed to a rigid support and the other end is fixed to the bob at equilibrium position. This is the equilibrium position of the simple pendulum. At equilibrium position, the bob does not oscillate and it hangs vertically downwards. So a simple pendulum, this position represents the equilibrium position, in which is the position the pendulum does not oscillate, it hangs vertically. This position is called as the mean position or equilibrium position. When the pendulum is displaced through a very small distance theta, displacement theta from the mean position, and if this pendulum is released, what will happen? The bob will execute simple harmonic motion. It will move to and fro about the mean position. So the pendulum bob will execute simple harmonic motion. Let us take L to be the length of the pendulum, which is the distance between the point of suspension and the center of gravity of the bob. So when the pendulum is in this position, at one extreme position, you have to understand that there are two forces acting on the pendulum. One force is the weight of the pendulum mg acting vertically downwards. Here the pendulum is not in the equilibrium position, it is in the displaced position. The angle of displacement is theta. Here in this displaced position, the weight of the pendulum mg acts vertically downwards. As the pendulum is suspended from a string, the tension in the string is acting along this direction. It is represented by the letter capital T. The two forces act on the bob of the pendulum at any displaced position as shown in the diagram. The gravitational force mg acts vertically downwards. The tension in the string which acts along the string to the point of suspension. Now, this mg can be resolved into two components. The normal component of the mg acting along the string but in the opposite direction is mg cos theta, which is represented as FAS. Okay, and the other component is the tangential component Fg sin theta, which is perpendicular to the tension. So Fg can be resolved into FAS, which is equal to mg cos theta, which acts along this direction, and another one is FPS, which is mg sin theta. The normal component of the force is along the string, but it is in the opposite direction. So we can write T minus FAS is equal to mv square by r, because this provides the necessary centripetal force. So T minus FAS is equal to mv square by L, where L is the speed of the bob. You know that FAS is nothing but mg cos theta. So T minus mg cos theta is equal to mv square by L. From the diagram, we can observe that the tangential component WPS of the gravitational force always points towards the equilibrium position. That is, direction in which it always points opposite to the direction of displacement of the bob from the mean position. So, in this case, tangential force is nothing but the restoring force. Now, we can apply Newton's second law along tangential direction. You all know that according to Newton's second law, the force F is equal to mass into acceleration. So applying Newton's second law along tangential direction, we can write m into d square s by dt square plus fps is equal to 0. Or I can write m into d square s by dt square is equal to minus fps. What is fps? Perpendicular component of the force, and fps can be written as mg sin theta. So m into d square s by dt square is equal to minus mg sin theta, where s is the position of the bob which is measured along the arc. Expressing the arc length in terms of angular displacement, s is equal to L into theta according to the diagram. So when you differentiate this, here s and theta are variables but length of the pendulum remains constant. So when you differentiate this, we can write d square s by dt square is equal to L into d square theta by dt square. Now comparing equation, substituting 1053 in equation 1051, we will get L into, that is instead of ds square by d square s by dt square, in equation 1051 we will get L into d square theta by dt square is equal to minus g into g sin theta, or d square theta by dt square is equal to minus g by L sin theta. Because of the presence of this sin theta in the above differential equation, it is a non-linear equation, differential equation, and we are assuming that the displacement is very small. When the displacement is very small, sin theta is taken approximately equal to theta, then the above equation will become a linear differential equation. So it will become d square theta by dt square. This equation will become minus g by L into theta. This is a very known oscillatory differential equation, and here we already know that this equation is of the form d square theta by dt square is equal to minus omega square into theta. So here instead of omega square we are having the term minus g by L. So the natural angular frequency of the simple harmonic oscillator or pendulum is omega square is equal to g by L, or omega is equal to root of g by L radian per second. So far in the previous sections we have studied up the formula for frequency of oscillations. The frequency of oscillations is given by the formula F is equal to 1 by 2 pi root of G by L, or the time period of oscillation T is equal to 1 by F. So the time period of oscillation of the simple pendulum is equal to 1 by F is equal to 2 pi root of L by G second. So these two equations are very important equations in the case of a simple pendulum. If L represents the length of the simple pendulum and G represents the acceleration due to gravity at a place where the pendulum is suspended, the time period of oscillation of the simple pendulum, or the time taken by the pendulum to complete one oscillation is given by T is equal to 2 pi root of L by G. From this equation we can give the laws of simple pendulum. Let us see what are the laws of simple pendulum. So from the time period of a simple pendulum we can able to see from this equation, if G remains constant, T is directly proportional to square root of L, and when L remains constant, T is inversely proportional to root of G. So depends on the following laws. We can say the law of length. For a given value of acceleration due to gravity, the time period of a simple pendulum is directly proportional to the square root of the length of the pendulum. T is proportional to root L for a given G, and this is called as law of length of a simple pendulum. The next one is called law of acceleration. For a fixed length of the pendulum, that is when L remains constant, the time period T is proportional to 1 by root G, that is time period is of inversely proportional to the square root of acceleration due to gravity. These are the two laws of simple pendulum. These laws were deduced only from this equation. Using this equation, T is equal to 2 pi root of L by G, and from this equation it is clear that there is no term mass of the pendulum is not included in this equation. So independent of the following factors, from the above equation 10.59, in the equation does not contain any mass term. So mass of the bob, the time period of oscillation is independent of the mass of the simple pendulum. This is similar to free fall. Therefore in a simple pendulum of fixed length, it does not matter whether an elephant swings or an ant swings, both of them will swing with the same time period. That is, the time period of simple pendulum is independent of the mass of the bob of the pendulum. And the next one, amplitude of oscillations for a simple pendulum with a small angle approximation. That is, if theta is very small, the time period is independent of the amplitude of oscillation. Next, we will see about oscillations of liquid in a U-tube. Consider a U-shaped glass tube which consists of two open arms with uniform area of cross-section A. Let us pour a non-viscous uniform incompressible liquid of density rho into the U-shaped tube to a height h. If the liquid and the tube are not disturbed, then the liquid surface will be in the same equilibrium position O. It means that the pressure at the two ends are the same, which is equivalent to the atmospheric pressure. Due to this, the level of liquid in each arm will be the same. By blowing air into one arm, one can provide sufficient force in one arm and the liquid gets disturbed from the equilibrium position O, so that liquid in one arm will go down and the liquid in the other arm will move up. So it creates a small pressure difference. This creates a difference in pressure which causes the liquid to oscillate for a very short duration of time due to about the mean position or equilibrium position, and finally it will come to rest. Why is it here oscillating? Means because there is a difference in pressure. Here the oscillations of the liquid column in this U-tube is also simple harmonic motion, and here the time period of oscillation is T is equal to 2 pi root of L by 2g second, where L is the total length of the liquid column in the U-tube.